The heart of recursion is a simple yet powerful idea. That is, to solve a problem, solve a slightly smaller version of the exact same problem, and then continue breaking problem into subunits until we have the smallest solution to build the answer to the big problem. Imagine you're trying to draw a Sierpinski triangle. It's one of those beautiful mathematical objects that seems complex, but is built from a very simple, self-referential rule. A Sierpinski triangle is made of 3 smaller Sierpinski triangles, and continue breaking this down. This is the core of the recursive definition. The whole is defined by its self-similar parts. If we kept applying the rule infinitely, we'd never finish drawing. Therefore, we need a stopping condition. So how does it stop? The first is when the triangle is too small to subdivide further. For instance, if its side length is less than 1 pixel, or if we've reached a certain depth of recursion. Looking at this pattern, we can define 2 fundamental rules of recursion. The base case, the stopping condition. This is the crucial anchor that prevents the infinite chain. It's the simplest possible version of the problem that can be solved directly without any further self-reference. Next is the recursive step, the self-reference. This is the rule that breaks the problem down. In this video, I am going to use these 2 simple rules to solve 3 different recursive problems. But first, we will use recursion to calculate the factorial of a number. Next, we will learn recursion through summation and apply our learn to solve binary search recursively. Let's dive in. Let us calculate the factorial of a number, say 5 factorial. By definition, 5 factorial equals 5 times 4 factorial, which breaks into 4 times 3 factorial, then 3 times 2 factorial, and times 2 times 1, which is the smallest number, called base case. Like we've seen before, in the world of recursion, you don't tackle the whole chain of multiplication at once. Instead, you observe the pattern. All this translates into 5 factorial equals 5 times 4 times 3 times 2 times 1. To do this step by step, we say 5 times 4 multiplied by 3, then by 2, and by 1. So, you've broken the big problem, 5 factorial, into 2 parts, a slightly smaller problem and a tiny bit of work. Let's talk about the recursive step, that is, the self-reference. This is the rule that breaks the problem down. For n factorial, the rule is n factorial is equal to a times the factorial of n minus 1. In doing so, I am delegating the problem to a smaller copy of itself. When you ask for 5 factorial, it asks for 4 factorial, which asks for 3 factorial, and so on. This is the first rule. Let's talk about second. That is the base case, the stopping condition. For the factorial, the definition gives us the base case. 0 factorial equals 1. When the call chain finally reaches factorial 1, it doesn't call itself again. It immediately returns the answer. Now, watch the process unfold in a call stack. Function calls 5 factorial. It sees the recursive step and checks if it is the smallest possible problem, then asks for 4 factorial. 4 factorial is called. Functions check it is the base case, then it asks for 3 factorial. 3 factorial is called. Check it is the base case, then it asks for 2 factorial. 2 factorial is called. Check it is the base case, then it asks for 1 factorial. 1 factorial is called. Check it is the base case. Then it hits the base case and instantly returns 1. This is the moment the unfolding of the problem stops and the folding begins. 2 factorial gets the answer 1. It completes its pending work. 2 times 1. 3 factorial gets the answer 2. It completes its pending work. 3 times 2. 4 factorial gets the answer 6. It completes its pending work. 4 times 6. 5 factorial gets the answer 5, 24. It completes its pending work. 5 times 24. The problem is solved not by a single monolithic command, but by delegating responsibility down a chain until the simplest part is found, and then letting the results bubble back up. It's an elegant expression of complexity, built from simplicity. Sum of numbers. Let's calculate the sum of numbers from 1 to n, say 5, is an excellent way to see the concept of recursion in action. The central idea is that the sum of a number 5 can be defined as 5 plus sum of 5 minus 1, which recursively calls 4, plus sum of 4 minus 1, which recursively calls 3 plus sum of 3 minus 1, which recursively calls 2 plus sum of 2 minus 1, which recursively calls 1. This equation perfectly embodies the recursive principle. To solve the problem for n, you must first solve the slightly smaller version of the problem. Our 2 recursive principle first is the base case, otherwise called stopping condition, the point where the problem is so simple we can answer it directly. Next is the recursive step. This is the rule for any number n greater than 0. It delegates the hard work to a smaller instance of itself. N factorial walked n plus sum of n1. Let's visualize this process of unfolding and folding in a call stack. Example, sum of 5. Let's see how the call chain works for calculating sum of 5. Sum of 5 is called into the stack. It checks if it's a base case, then computes 4 plus sum of 4. Sum of 4 is called into the stack. It checks if it's a base case, then computes 4 plus sum of 3. Sum of 3 is called into the stack. It checks if it's a base case, then computes 3 plus sum of 2. Sum of 2 is called into the stack. It checks if it's a base case, then computes 2 plus sum of 1. Sum of 1 is called into the stack. It checks if it's a base case. The results now bubble back up the chain, completing the pending operations. Sum of 2 receives 1. It calculates 2 plus 1 equals 3. Sum of 3 receives 3. It calculates 3 plus 3 equals 6. Sum of 4 receives 6. It calculates 4 plus 6 equals 10. Sum of 5 receives 6. It calculates 5 plus 10 equals 15. The final answer, 15, is returned. Binary search. To explain binary search recursively, we view the problem of finding a target value in a sorted list as a continuous process of solving a slightly smaller version of the exact same problem. Let's use this simple example. Given a list of elements, how do we use binary search to find the number 42? Binary search works by first checking the middle element. M, middle element here is 34, is less than target 42, so binary search checks the upper half, right side. Middle element here is 67, which is greater than 42, so binary search checks the lower half, right side. Once again, binary search recomputes middle element 42 is equal to 42. Base case. A reached. Return success index. From here, we know that recursive binary search works by immediately eliminating half of the possibilities. Let's visualize the call stack, just like we explained earlier. Let's say we're searching for 42. Call 1 middle element 34 is less than 42, so recursively call on the upper half right side. Call 2 middle element 67 is greater than 42, so recursively call on the lower half right side. Call 3 middle element 42 is equal to 42. Base case. A reached. Return success index. The recursive logic is the elegant mathematical expression of this halving strategy, guaranteeing the problem is solved in logarithmically few steps. Thank you.